So this idea of work, we now know how to calculate it if we know a force, or if we know a force function, or if we know a graph of a force. But why would we even need to do this in the first place? Well, it only really comes into play when there's some sort of external force acting on the object. Again, the three ways of representing that force. And then a friction is part of the system. Then this is how we're going to incorporate that. So if there's an applied force, and many times that force helps the object's motion, and so the work is a positive amount, and so our final energy ends up being greater than our initial energy. So looking down here, whatever our initial amount, we would be adding something. This would be positive. And so this final amount would end up being a greater value than what we started with, instead of being equal. If there's work being done that's negative, meaning the force works against the motion, friction would be a great example of that, then all that changes about our setup is that the W, the work value, is negative. And so then your initial value would be bigger than your final value. But by just kind of adding in this plus W to the left side of your setup, you are good to go in terms of incorporating work into your setup. Another way to represent this is to say that work represents the change in energy, and some people do prefer to do that, but it does require you to make sure that your signs are all perfect and everything. I like this method here because it builds off of what we've already been doing in terms of energy. So taking a look at a couple of examples that use different methods of finding work, if we're given a graph of how force changes with position, we can use that graph's area. So we're going to find this area here and this area here, the area bounded by the graph and the x-axis. That'll determine our work value. So let's go ahead and do that first. Work is the integral of f dx in this case, which we are going to get just by looking at the area of that graph, the bounded area. And so in this case, we would find the area of that first triangle. So that's going to be 1/2 times the base, which is 2, times our height, which is 4. And then our next triangle, some people like to put a negative here, which you can. Just think about I'm subtracting because it's below the axis. Or you can say that the base is 1 and the height is negative because it drops below the axis. So I'm going to put a -2 here. But either way, we get 3 joules as our work. So that's the amount of energy that's being added or taken away. In this case, it's positive, so it's being added to the original energy. So summing up the energy I started with, if I take that amount and I combine it with this extra amount of energy, this work, that tells me the final amount of energy that I have. And so in this case, there's no talk about potential energy. It's all about kinetic speed is what the problem is asking about. So we know the speed at 3 meters. So we know the final speed. We are trying to find the initial. So we know that final. We are trying to find the initial. And again, we know the value of work from the area. So just plugging in values here then, 1/2 our mass. This is our unknown, plus 3. That's our work value that we found up here. 1/2 times 5 times 2. And then just do our algebra, and this should come out to be 1.67 meters per second. Again, it doesn't tell us a direction. It just tells us a speed. Let's take a look at one more example. So in this case, we would take a look at this and we would see that there is a function given. So that gets us thinking calculus ideas. And since it is a function of force with respect to position, that's how we're going to know that this is an energy question. Instead of earlier, we might have seen this and thought more about using motion ideas like acceleration and velocity and position and so forth. So, but the fact that it's force as a function of position, again, I can find the work by calculating the integral of f dx, since that's the variable defined. And in this case, because I'm actually given the function, we would just stick with this notation. I'm just going to set this up so that would be my integral that I'm trying to evaluate. And because I'm finding the energy that's gained or lost as it moves between two very specific positions, I know my bounds. That's a definite integral. And so we would integrate by increasing our exponents, 1.2 x squared, so I raise the exponent of x to x squared, and then I divided by that new exponent, 2, and then I would raise my exponent to x cubed and divide by that, and it gives me 1.6 x cubed, and that's what I'm evaluating between 1 and 2. So that would be 1.2 times 2 squared and 1.6 times 2 cubed. And then for my lower bound, 1.2 times 1 squared, which is just 1, so I'm just going to leave it off. And 1.6 times 1 cubed, again, leave that off. And this comes out to be 14.8 joules. And then similar to what we had in the last question, this is all about kinetic energy. We know the initial speed this time because that's 4 meters per second at x equals 1. That was our initial bound. So our initial energy plus work, again, this time my work is a positive value, so I'll be adding a positive number, the 14.8, and my energy values are all kinetic. This would be another way I could simplify my work by stating that that's the type of energy I'm working with. And then 1/2 times 3 times, and again, I know my initial speed, and I know the energy being added to the system, so that total amount is going to go up. So I'm anticipating that my speed is going to go up when I finish my calculation. And sure enough, it comes out to be 5.1 meters per second.